Hi everybody. I'm going to do an example of moment of inertia, and it's going to involve center of mass. And then later I'm going to do an example that involves not just point particles but an extended rigid object like a thin rod. Alright, let's start with this example that I have here. The red line is the rotation axis, and the little dot there is a particle that's attached to a massless beam. And let's pretend that we're just going to rotate this thing around this axis. If we want to figure out the moment of inertia, here's the equation up here. So that would just be 1 kilogram times 1 meter squared, and we get 2 kilogram meters squared. So let's add on another mass here. Let's say there was some more mass out here at the 2 meter mark. Again, 1 kilogram, and I would just add that on to the other moment of inertia I found earlier. So it's now 1 kilogram times 2 meters squared, which gives me 4 kilogram meters squared. And I'm going to add on one more, again pretending that the beam that's connecting these is massless. Now I'll add that one on, and it's 1 kilogram times 3 meters squared. Hi everybody, I'm going to do a couple of examples of moment of inertia calculations. The first one's going to involve just point particles and the concept of center of mass, so I can illustrate something about how the distance from the rotation axis really does matter. And the second example is going to involve a thin beam that is not just a nice, separated set of particles. So the first example here, you can see, has the rotation axis here in red in the dashed line, and then we're going to have this little particle here, and let's pretend that it's just going to rotate around this axis. This little line here, let's say, is a massless beam. And so if I want to do the moment of inertia calculation, here's the equation. So that would be 1 kilogram times 1 meter squared. So I'd get 1 kilogram meter squared. So now I'm going to add on another particle here, again with a massless beam. And we're going to say it's another 1 kilogram. So now I would just add that on to my first moment of inertia. So it's 1 kilogram times now 2 meters squared. And I get 4 kilogram meters squared. So you can see that adding one more particle at double the distance actually gives us a lot more moment of inertia. So my total is 5 for this system. And if I add on a third particle, 3 meters from the rotation axis, again 1 kilogram, I can add that on. And so now I have a total moment of inertia for this 3-particle system of 14 kilogram meters squared. So I was looking at this and I thought, well, couldn't I just take these 3 particles and find their center of mass and treat the 3 particles like one? We've done that before in this class, where we find the center of mass and pretend like all the mass is there. So if you did the center of mass work, you should find that the center of mass of these 3 particles is actually right here in the middle. And so let's pretend like all the mass of those 3 particles is right here. And so this is a heavier particle of 3 kilograms, and that's the center of mass of my system on the top. So I wonder what the moment of inertia of that would be. So that's at the 2 meter mark. So now I've got 3 kilograms times 2 meters squared, and that's 3 times 4, so I get 12 kilogram meters squared. So my question for you is, what's going on here? Why are they not the same? So one way we could try to answer this is to try and reverse the process and break apart the 3 kilograms. So let's try and do that. So let's do this. Let's break off 1 kilogram of that. Let's say we're going to keep 2 kilograms here, but let's move 1 kilogram back to here, to the 1 meter mark. So we know that that should reduce the moment of inertia, because the closer you get the mass to the rotation axis, the smaller the moment of inertia. So let's calculate that quick. That's 1 kilogram times 1 meter squared plus now 2 kilograms times 2 meters squared, and we should end up with, we get 9 kilogram meters squared. So we went from 12 to 9. Now let's do this one more time. Let's keep our 1 kilogram here, and let's break apart this 2 kilogram guy back into our 3 original pieces. So we've got and now working out that same calculation from before, we get 14 kilogram meters squared. Alright, so I hope you noticed that transitioning from this setup to that setup took away a little bit of the moment of inertia. It was 3 kilogram meters squared. We went from 12 to 9. But transitioning from this setup to that setup added to our moment of inertia. It made it bigger because we slid some of the mass farther away. And you can see that that actually added 5 kilogram meters squared. And the reason there is that this, this transition right here, it makes a bigger difference in the moment of inertia, because if you look up here at the equation, we've got this r squared in the equation. So farther away is going to matter more. So long story short, we cannot simplify this system up here into this system right here. Okay, now let's look at the case of a thin rod. So I'd like you to imagine that, again, the rotation axis is on the left, and this rod is very thin. So we're going to pretend it doesn't have any thickness. It's just like a thin line. It doesn't have a height, even though I drew a height just so you could see it. And then we're going to rotate it around this axis here, kind of like that way. Sort of like you have a baseball bat and you're holding onto the end of it and twirling it around. Alright, so how do we find the moment of inertia of this? Well, if you look at our equation here, that's for point particles. And it's not so easy with an extended object like this, because there are many r values here. There's not like one piece of mass at 1 r that we can clearly see. So one thing we could try here is we could try just breaking it up into pieces. So let's first try just breaking it into a couple of pieces. So now I can see 2 pieces, and I might think that maybe I could just simplify this and say, okay, well, this system's just like 2 particles. If I say that the center of mass is where all the mass of each chunk is. However, we just saw that that causes a problem, because the mass on this side of the center of mass is contributing more to the moment of inertia than the mass on that side. So that kind of causes a problem there. One thing we could try to improve that would be to break it up even smaller. So let's say we broke it into 4 pieces. And again, we could say these are the locations of the center of mass. And we still run into the same problem because the mass on this side of the center of mass is contributing more to the center, or more to the moment of inertia than the mass on the left side of the center of mass of each chunk. However, if I make the chunks smaller, then the difference between this, where the center of mass is and the mass on either side of it, here and here, gets smaller and smaller. So if I break it up even smaller, then for each given chunk, that's not going to be that much different for the R value of the center of mass. I'll call that R center of mass. This is, R for the mass that's farther away, and R for the mass that's closer. So if we keep breaking this up smaller and smaller, we're going to get a better approximation of the moment of inertia. We're just going to have more work to do because there's lots of pieces to add. So thankfully there's a great method called calculus, and so I'm just going to do a quick little derivation here for how to chunk things up. You've probably done this quite a bit in calc class. So I'm just going to take my equation and I'm just going to turn it around. And just say Ri squared times the mass, like that. And I want to take the limit as these, oops, I didn't write the limit in the right spot here, but I'm going to take the limit as these little chunks of mass approach 0. So if you do that, what this turns into is an integral of r squared dm. And dm is just a tiny chunk of mass. I like to call it the dinky mass because it's so small. And there's a little d there. So this we can use for a rigid object. And this is a pretty straightforward integral, just the squared value there. So let's relook at our beam now. And we need to figure out how much mass these little chunks have. I'm going to give this beam a mass of m, and I'll say it's a length L. And so the density, let's see, the density of this beam is m over L. It'd be kilograms per meter if I did use units. So however thick this little chunk is, I'll call dinky r, a little change in position. So my dinky mass is going to be however wide that thing is, dinky r times m over L. And if you could verify that with the units. Dinky r would have units of meters, this would have units of kilograms, and L would have units of meters, and so the meters would cancel out. So now I'm going to take the integral here. M over L, M and L are constants. Oops, I skipped a step. Integral from 0 to L, r squared dot dm. And I know dm is dr times m over L. And I can pull out the m over L. And you should know how to evaluate that from calculus class.